Okay, we can say the predicates. We have learned this one in chapter 1.1. Predicate is statement that contain some variables. For example, here we have px is either true or false. X is greater than 3. Okay, and for example, here we have p is a predicate for the left side. Left hand side is the predicate, and right hand side is the statement. Okay, px x is greater than 3. Okay, and then x, we have two variables, x equivalent to y plus 3, because we have two variables. And then for we have the three variable, we have x plus y is equivalent to z. Okay, and then if we want to know, we insert the values. For example, here we propose true or false, x is greater than 3 is unknown, because we do not test. We not test yet, not test yet. So we go by P3. We put the 3 here. 3 is equivalent, 3 is greater than 3 is false. Okay, this one is proposition, and then we continue by P5. Okay, and then 5 is greater than 3 is equivalent to true. Okay, we must put the value. How to measure the predicate? We must put the values. Okay, for the proposition. Okay, and then a predicate become a proposition if we fulfill the two condition here. First one, we assign the specific values like we did. P, okay, x, okay, px is either true or false. Okay, and then secondly, we quantify. We quantify. Okay, we quantify the statement. Okay, for example, px. Okay, px, x is the variable. Okay, we have one variable and x is greater than 3. What are the truth value of P4 and P2? Okay, this one is first one. Secondly, we have two variable here, x and y. X equivalent to y plus 3. What are the truth value of Q 1 and 2 and Q 3 and 0? Okay, so Px, x is greater than 3. Okay, we have value here. Okay, 4 and 2. Okay, okay, when P4, okay, 4 is greater than 3 is equivalent to true. And then P2, 2 is 2 greater than 3, false. Therefore, P4 is a proposition and P3 is not. Fayad, is it okay for you? Fayad? Okay ke? Tulislah nota sikit. Kesian saya. Banyak saya buat. Palette apa saya beli untuk kamu. Nanti tolong upload nota. Nota untuk kamu, bukan untuk saya. Saya memang faham tak faham, saya nak bagi kamu fahamnya. Tapi kalau kamu tak faham nanti, bila exam nanti kamu tak dapat jawab, kamu salahkan saya pula. Okay, and then here ada berapa variable kat sini, Liana? Liana ada berapa variable? Norina, Liana, ada berapa variable kat sini? Ada dua, X and Y. Kamu main game ni. Kamu masak-masak ke? Ke kamu tidur? Ha, saya tengah buat roti. Okey, tak apa. Kamu masak untuk keluarga Dah ada anak Okey, kita ada X ada dua When X equivalent to Y plus 3 Okay, and then we put the values 1. Okay, equivalent to 2. plus 3. 1 is equal to 5, false lah. Okay, that's why the Q is a proposition. Okay, we test the value either true or false. Okay, then here we introduce to you the quantifier to quantify the proposition or the statement. Okay, first we have a universal quantifier like this, and then we have existential quantifier like this. Reverse E. This one is reverse E, and then this one is not existential. This one is a member of. This one is basically for a set. Okay, for example, here we have Px, x is greater than 3, and for U is the universe of this course. Universe of this course, U is a domain, domain of variable. What is domain of the variable? Domain of the variable is the basically is the problem, a problem that you you assign. You assign. For example, here U is a positive integer. Okay, positive integer. We have 1, 2, 3, 4, 5, 6 until exponent value, and then when you go by the x uh, equivalent to 3 or 4, it is okay. When you put the 3 is greater than 3, okay, it's null. Okay, and then if you put 4 is equivalent is greater than 3 is yes. Okay, any positive number or positive or negative number. Okay, and then we have the predicate Px is true for all of value x in the universe of this course. Okay, we have for all a x and for Px. We can say for all same, for every x is same. Okay, for example, here we have for all y, for every y. Okay, for every y, for all y is same. Okay, and then the variable x is bounded by the universal quantifier producing a proposition. It must be bounded. Bounded mean it must be at the same beside the proposition. Okay, beside the quantification. Okay, here and here is beside. Okay, let me explain about the bounded and free variables. You have bounded and free variables. Okay, the meaning of for all we have properties. Okay, we have some properties for bounded and free. Okay, you put this one like this. Uh, okay, we have existential x. X is a member of y, and existential y. Then we have negation y. is a member of X. Okay, which one is bounded, which one is free? Has it? Has it ada? Mana yang free, mana yang bounded? X bounded. Hmm. Okay, here, this one and this one are bounded. This one is free because there is no quantifier here. Clear? Dia tak ada quantifier. There is no quantifier here. It is free. When you have the quantifier here and also here, because we have here we have the commutative. Okay, in here it, it is called bounded. Okay, clear ke? Saipul, okay ke? Saipul Nizam. Saipul. Okay, okay, and then we have universal quantification. Okay, for universal quantification, we have for every x that integers x is greater than 0 is true lah. Equivalent to true, and then when we continue x1, 1 is greater than 0 is true. Okay, to true until exponential are true lah. Okay, because px for the variable, and then we have the statement here. Okay, statement and conditional. For the condition x must be greater than 0. Okay, for px, for predicate x, variable x, x must be greater than 1. And u is a positive integers. Okay, when 1 is greater than 1 is false. For all integers we refer to positive integers, x must be greater than 1. Okay, and then for all x, px, this one are false because not all values of px x greater than 1 are true. One are false lah here. Amar Ashraf okey ke? Boleh? Boleh ikut? Uh, ni this one for all. For all mean for every item and for all item must be true. Example what is the truth value of for all x for px? What is the truth value for all x qx, and x has an account on tabung haji? What does for all x rx mean? Okay, for all x, px is equivalent for px for variable 1 and variable 2, x2 and so on until the variable xn. For the n is also called for the conjunction. If the element in the universe of discourse is the domain of the problem, can be listed as the u is a member of the set of x1, x2 until xn. Okay, for all x, px for the predicate and variable x is equal to p x1 and conjunctive. And u is positive integer not exceeding than 3. And px, okay, and then this one x the power of 2 are less than 10. Okay, we have 1 power of 2 through 2 power of 2 through 3 power of 2 through 4 power of 2 false because this one is 16. That's why Okay, true, 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 and false. And true implies false is false. Okay, because for all value must be true. Okay, okay, and then existential quantification. Existential mean there exists an x such as px that is at least one. For example, you have false, 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 and then you have one true, valid. Because not all of the values are false. Okay, they have one values here are true. And the variable x is bound by the existential quantifier producing a proposition. This one also same. Okay, another example of free and bounded variable. Okay, we have existential x. Okay, which one is bounded, which one is free? Kalista? Kalista? Which one is bounded, which one is free? Yeah, and the free is x. Okay, yang ni free. Lagi? Itu saja. Existential one free. Oh, dia tak free. This one is not free because bounded by existential. This one is not free because it is bounded by the predicate. Okay, the only free variable is y because ey is not existential. This one is member. Member. Only free is y lah. X is bounded. Okay, and then existential quantification. This one I have explained. Okay, we have existential x, px. Okay, and then the conditional statement x less than 2 and u must have positive integers lah. Okay, and then we have existential x px is true lah because we have a false and then only one is true lah because not all the values are false. Okay, that's why for some x that is positive, integer x is less than 2 is true. Okay, because 1 less than 2 is true, 2 less than 2 is false, and so on. Okay, this one example, px x greater than 3, what is the truth value of existential x, px, and so on. Okay, okay, for existential quantification, we should have disjunction. Disjunction. Please remember, for universal, for all, we should have conjunction. For existential, we should have disjunction or. Okay, because and all of the values must be true. For this disjunction, all the value can be true, can be false. Not all. Not all. Okay, we have a positive integer not exceeding 4. p x. Okay, and then the statement x power of 2 is greater than 10. Okay, what is truth value? Okay, and then bound variable, if a variable is quantified, if a variable is being quantified, and free variable in either bound or assigned with a specific values. For example, we have for all x, px, existential x, q, xy. Scope of quantifier, part or logical expression to which quantifier is applied. Okay. Okay, and then we have negation. Negation, either you look the symbol like this, is equivalent like this, tilde. It's same, negation. We have a negation for all, and we have negation for existential. Okay, for example, we have px for the variable, whereby the condition x has taken course in calculus. Okay, and then negation universal predicate is equivalent to no negation existential negate the predicate. Okay, this one equivalences. Same. Okay, for example, negate existential x px is equivalent to no negation for all x, but for the this one we have negate the predicate. Here we negate the predicate. Okay, until the end we have for all x negate px is equivalent to no negation existential x px. Okay, this one is the same. Okay, you just reverse. Reverse this one. For all, you have negation x. Okay, this one is negation. You put qx is equivalent to. Here you change negate for all x. Here negate qx. Okay, this one is when you want to translate to English. Many ways to translate given sentences from the uh, uh, quantifiers to English. The goal is to produce a logical expression that is simple and that can be easily implemented in subsequent reasoning. You have to do three main steps. First one is clearly identify the appropriate quantifiers. Secondly, introduce the variable and predicates. Okay, this one, variable and predicate. And then three, translate using the quantifiers, predicate, and logical operators. This one is depend on situation. Some of the students ask me how to use the quantifier, how to use when to use the predicate, and when to use the logical operators. It's up to the logic. For example, here every student in MTK has studied discrete structure, and then assume that the universe of this course, the domain is all student in MTK. And then solution number two, assume is equal all people, and then quantifier for all, and then predicate. We have logical operators. Okay, every student is for all. For all, it's not for some. In MTK has studied discrete structure. Okay, all student of MTK is universe of this course. First, you need to identify the universe of this course, U. Okay, and then PX. Okay, PS for the variable. For predicate, you need to subscribe. You need to explain the variable x. X has studied discrete structure. And then for all x, px. Every student, or you can say all student, studied MTK 3013. And then for secondly, all people, px, x has studied ds. For all x, px, all people have studied discrete structure. And then if you have qx, q is a student in MTK 3013. And then for all x, qx implies px. Qx is the student, implies for the general. General is the conclusion. This one is hypothesis. Okay. For every x, okay, x is a student, implies px for all. Okay. That means x is a student. Okay. In MTK, in the discrete structure, implies has studied the discrete structure. Okay, another example, some student in this class has visited Mexico. First solution, you assume you for the domain of this course, all student, and then solution two, all people. Okay, in a final assessment letter, you can use either one. This one also correct, this one also correct. More example, CX, X is computing students, MX, M for the multimedia student, S, X is a smart student, and for the domain, all of student in MTK 3013. Okay, every student is a computing student. Okay, for all X, CX. Okay, C is computing. Okay, and then nobody is a multimedia student. You need to put the negation existential X, MX. Padam. Okay, and negate existential X, MX. And then for all computing students are smart students. When you go by the computing student for all X, and then we have CX for the computing students, and then are smart student because of the implication imply, you should put the implication like this as X. Okay, this one from the uh, conclusion to the hypothesis. And then sum, okay, existential X. Okay, and then we have computing students are smart students. Okay, C X N because some unit conjunction are smart student and S X. Okay. Okay. Later, I used to give to you the exercise for this. Don't worry. And then nobody is a multimedia student. Nobody existential X MX. Okay, existential there is does not exist some student. Okay, and then everyone is not a multimedia student. Okay, quantifier, and then we have the predicate. Okay, quantifier universal, and then we have the predicate. Not, you should put not here. Wait, eh? Okay, and then we have another one is determine the true value for u for z. Z is rational numbers, and then existential n, 2n is equivalent to 3n lah. Okay, and then determine the true value of u for r. Okay, and then we have negate existential n, x equal to 2 is equal to negative 1 lah. Okay, exercise 17 page 47, you don't need to do lah. This one is just error lah. And then we have a nested quantifier. Nested mean you have the drawing problem. Wait, I close this one first. Okay, this one, and then is not multimedia. Okay, and then use implication or conjunction. Universal quantifier usually take implication. Universal take the implication because it is a conjunction. And then all competent students are smart students. Okay, this one is correct. Implies here. Correct. Okay, and then conjunction is incorrect lah, because implication means general. Okay, secondly, existential quantifier usually take conjunction, conjunction and. Kenapa ada kat sini dia punya ni? Tak boleh padam tak? Tak apalah. Saya tutup sekejap yang ni. Ada problem sikit sorry Okay, baru okay. Okay, existential quantifier usually take a conjunction. Conjunction mean and lah. Okay, because it not implies uh, for the general, because not every element of universe of discourse you, okay, are true lah. Okay, this one is incorrect. Zul Jamal boleh ke? Baru datang Zul Jamal. Baru sampai ke? Eh, okay. Kalau ada internet connection, tengok YouTube saya. Okay, and then no computing student is multimedia student. Okay, this one, if X is computing student, then the student is not a multimedia student. Okay, you can use uh, implies, okay, for all, because it is for all. And then there is no is it a computing student who is also multimedia student. Okay, you can use conjunction, okay, like this. And then if any multimedia student is a smart student, okay, for any X, multimedia student MX, and smart student SX is CX, computer student. Okay. Okay, now computing student is a multimedia student is you use the De Morgan law. Okay, for all X equivalent to existential X. And then every computing student CX is not a multimedia student MX. First, this one you use the hypothesis and conclusion, and you use the implication equivalent negation of the quantifier, and then you use the De Morgan law, and then you have finally you have no computing CX and MX multimedia students. Okay, you negate. We have the for all universal quantification, and use the negation for the implication equivalences and negate. And then for the universal, for the negation of quantifier, you have negation X. You negate the predicate here. Okay, so you finally got existential X, Cx, and Mx. This one is De Morgan law. This commutative. Commutative. Okay, and then no computing student is a multimedia student. Is equivalent. Every computing student is not a multimedia student. Okay, for every you cannot use the conjunction. You must use the implication. Okay, implication. And then you have the negation of quantification. And then lastly, you use the implication equivalences for the hypothesis and conclusion. Hypothesis and conclusion. And lastly, you use the De Morgan law. Okay, negation, existential X, computing student X, and multimedia student X. Okay, is same here. Okay, this one. Okay, and then we have a nested. Nested pxy. We have two variables here. X plus one. U is R. R is the rational numbers. Okay, for all x existential y, p x y. We have two variables here. Okay, for all pair x, y, both quantifier type is the same. Okay, we have here for all x, for all y. Nested. Nested means you have two quantifier of two variable, either x or y or x and y. Okay, and then for every x is y such that p x y different type of quantifiers. Okay, for all x for existential y, p x y is not the same for the existential y for all x. This one first is not same for this one. Also same for the existential first, and secondly for all y. It's not the same, but it is same if you have the same type for existential x, y, p, x, y is same if you just change the position. Existential y, existential x, p, x, y. Same. If you have the same type. For different types, okay, it's not same. Okay. Both quantifier type must be same. Must be same. Like this can for all x, for all y is same for all y, for all x. Okay, and then translating statement with nested quantifiers. Okay, u is a real number for all x, for all y. X plus y is equivalent to y plus x. X plus y, existential y, x plus y is equivalent to 0. And then for all x, for all y, x greater than 0 and y less than 0 is equivalent to x, y less than 0. The same goes here. Our student in CS2813. CX is a computer, has a computer. F, we have two variables, x and y are friends. This one on people, because this one refer to the students. Okay, for all x, C x or existential y, C y and F x y. Okay, we must use the conjunctive. Okay, this one integer positive is another example. If the quantifier are the same type, then order doesn't matter. This one I have explained. If the quantifier are different types, then order is important. Okay, it's same. X for all x for all y is same that for all y for all x. This one order is important. It's not the same for. Ni tak sama. This one is not same. Azlina boleh? Nur Azlina boleh? Azlina boleh ke? Iza boleh Iza? Nur Iza? Nur Iza? Dia tak sama saya dah explain tadi. If the quantifier of the same type for all x for all y is same for uh, for all y and for all x. And then last one, last slide. Wait, hang a little bit. Dia hang sebab lama sangat. Example, z is integers. We have z integers, x, we have two variables here, x plus y is equivalent to 0. Okay, for all y, for some y, for all x, and for all x, for some y, that exists is false. Okay, but for this one is true. For every x when y is negative. This one false because not for every only when y is negative. Okay, for example, here we have it's not the same. This one for all x existential y, and then we have q and y is true. It's not same with for some y for all x xy is false. Okay, because if you see here x plus y is equivalent to 0. Okay, 0 0 0 0 0 for some y for all x. Okay, is false because all of these are uh, 0. And then for every x there is y such as x plus y is equivalent to 0. Okay, 0 0 0 is true for all. For all it's true. This one for some is false. Okay, because it is must be 1 here that this statement goes to true. Okay, I think that's all for today. Okay, I hope you can understand a little